Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be looking at Chapter 16 on discriminant analysis. Discriminant analysis is a strategy for finding linear combinations of the features that we have that best distinguish subgroups or subspecies or populations or any way that you define groups in your analysis. Let's start by looking at an example. Along the horizontal axis, we have feature 1, and along the vertical axis, we have feature 2. And when you plot the two populations, subspecies 1 and subspecies 2, they make these two bivariate normal elliptical clouds of points. Now the question we want to answer is, can we find one direction, one linear combination of both features 1 and 2 that will best distinguish these two groups? And in this case, you can see if we draw a line along this negatively sloped diagonal, that should separate them the best. So I've drawn that line down here, sort of out of the way, and I've also imagined that you take these two ellipses and you project them down into the left onto that plane. Then you get these two normal distributions. The one on the left or above is for group 1, and this lower one is for group 2. And so we've taken these two clouds and we've just projected them down into the left onto that plane to see those two groups. Now that projection gives us the best separation between these two groups. So now that we reach a decision point. So along this direction, what decision point best classifies group 1 and group 2? Well, it's where I've drawn this one line. That will provide the minimum misclassification. So I've taken that line and I've drawn it perpendicular to this, the line that best distinguishes them. I've drawn this one line, and that is the rule. So anything above that line, above and to the left, will be classified as species 1 or subspecies 1. Anything below and to the right of that line will be subspecies 2, and that's the basic idea of discriminant analysis. Finding this canonical direction. So, and we can look at this for more than 2 features and more than 2 subspecies. I was just giving a simple example. So canonical discriminant analysis. Also canonical correlation. I prefer to emphasize the connection between canonical discriminant analysis and MANOVA because the techniques are essentially identical. MANOVA tries to perform a hypothesis test of which, are the means for groups different or not. And Roy's root gives us the canonical directions that best discriminate the groups, and those are actually the canonical directions that are given in discriminant analysis. All right, so that is pretty much what those paragraphs said. The first linear discriminant function, which I'm calling canonical 1, is the linear combination of the original features that gives the most significant f-test for a null hypothesis of no group differences in an ANOVA. So if you want to ask, are the groups different, this is the direction that gives you the most power for detecting a difference. And then canonical 2 is the second linear discriminant function that will give you the most significant f-test that is uncorrelated with that first direction, canonical 1. and so on. So you'll get canonical 1, canonical 2, and so on. And the number that you'll have is the minimum of P, which is the number of features you have, or one fewer than the number of groups that you have. So in the example above, where we had 2 features, P, and 2 groups, the number of canonical discriminant functions that we could write is the minimum of 2 and 2 minus 1, which is 1. So we could only have one canonical function, and when I page up, it was this one canonical function in this downward sloping direction. All right, let's look at an example that is an unusual example. Oh, maybe there's one more point up here. And that last point is the same as in principal component analysis. You can always multiply the loadings, these A1, A2, and up to AP values by -1 and get the same direction. In the case of the example here, this canonical line can be thought of being an arrow that's pointing down and to the right, or an arrow that's pointing up and to the left. The direction doesn't matter. Whether it's up or down. So up or down doesn't matter, but that direction in the two-dimensional space does matter. All right, let me page back down and get to the riding lawnmower example. So out of a book by Johnson and Wickern, the manufacturer of riding lawnmowers wishes to identify the best prospects of buying their product using data on incomes, this is house incomes, and lot sizes, that's the size of a person's house, of homeowners. And so they've looked at a random sample of 12 people who currently own lawnmowers and 12 people who currently do not own lawnmowers. And they want to know what distinguishes these two groups. If I'm going to go door to door selling lawnmowers, I think that's seriously the scenario that we're in. If you're a door to door lawnmower salesman, then you might want to know, am I more likely to, how am I going to maximize the chance of each person I go to giving me a sale? So we've got data on incomes, lot sizes, and whether they own their lawnmower or not. And I'll go ahead and plot this data. The blue triangles are owners, and the red circles are non-owners of lawnmowers. The horizontal axis is incomes for these people, and the vertical axis is lot sizes in thousands of square feet. So it looks like people don't buy a lawnmower if you've got a small yard, less than 5,000 feet. But once you get to about 6,000 or 7,000 feet, people are buying lawnmowers, and maybe people just don't have lawns bigger than 12,000 square feet. So there's this sweet spot of sort of 7,000 to 12,000 feet. So that's good to know. And then the people who are the owners tend to be a little more wealthy, so these triangles are shifted to the right, and the triangles are shifted up relative to the red ones, so wealthier people with larger lot sizes. All right, not a surprise perhaps. Here's a scatterplot matrix of all the features, and in terms of lot size and income, this is basically the same plot as we saw above. But we see some distinctions for lot sizes and for income. But what we want is a single direction that gives us the best discrimination between owners and non-owners. Looks like there's already some discrimination on the individual variables, but we can do better. All right. So again, we're in a situation where we've got two features and two groups, so we know we only have one function for, or one canonical direction that we're going to estimate. I'm fitting a linear model just to do an analysis of variance test on the individual features. So if we look at the difference between incomes for owners, it looks like there's a difference there. Similarly, if we look at differences between lot sizes, looks like they're a little bit lower. It is significant. Here's the p-value for whether you're an owner or not, based on the lot size. So in both directions, we are finding significant results. Maybe we'll just take a look at these p-values, 0.004 roughly, and 0.005. If we fit a multivariate ANOVA, Roy's root is going to give us the direction that is the best way to distinguish these two groups. And notice the p-value of 0.0003. So it's we found a direction that does even better by taking a linear combination. And now we are going to use the CAN-DISC package, so the canonical discrimination package, and we're going to run that on the linear model object that we created above. Let's go find that object. lm.mower. So this was where we fit the linear model, and we column binded both response variables on the left. I'm going to page back down. And we're running the canonical discriminant function on that linear model object. And it gives us the canonical discriminant analysis. We have a canonical r-squared value of 0.5. We have an eigenvalue, and this explains 100% of the differences. We only have one canonical variable. If we had multiple ones, it would be listed here. Furthermore, it gives a likelihood ratio test of whether there's a difference between the two groups, and the p-value here, 0.00004, suggests that there's a significant difference between the two groups along that direction. The canonical discriminant object has lots of objects inside of it, and we're going to use some of these in a moment. So the coefficients raw object gives the coefficients for the canonical discriminant linear combination of income and lot size. Notice that both these signs are negative, which suggests that the direction is going to be up and to the right, or down and to the left. So these two variables go together. The means along that canonical direction are the two means for non-owners and owners. So because these two coefficients are negative, as you increase canonical direction 1, you have to decrease income and decrease lot size. So as canonical direction 1 increases, both of these things are getting smaller, and that means those are poorer, not poorer people, but people with less income and smaller lot sizes. So those are our non-owners. When you go in canonical direction in the negative direction, that means negative, negative, we're increasing incomes and we're increasing lot sizes, and those are our owners. And along that direction, these are the means for those two groups. Maybe a way to relate that is if I scroll way up to this original example, what we found, of course, our distinctions are in an opposite direction. This isn't very helpful, unfortunately. Our canonical direction is actually like the slope of this line going down and to the left or up and to the right. So this may be a little bit hard to see, unfortunately. All right, I wish I could have made a better example. I would have drawn that on the board. All right, so here is the canonical function we found. Can1, the dotted line, is the canonical direction. And this 0 point along this axis, if you go to the left about 1 unit or so, that's the non-owner mean. And if you go 1 unit to the right, that's the owner mean in that direction. If at this 0 point, where I've drawn this solid line perpendicular to canonical 1, that is the decision point of whether to classify to the left as non-owners or to the right as owners. And we'll see more of that classification using discriminant analysis in the next chapter. If you plot the data in the direction of the canonical variables, you can see how little overlap there is, perhaps particularly in the box plots. You can see that the boxes don't overlap at all, and it's just the whiskers that overlap the boxes just a little bit. Comparing that to the scatterplot matrix that we started with, here you can see the boxes for lot size basically are the same value, and the box plots for the boxes for income overlap just a little bit. So we're getting better separation using our canonical function. The standardized coefficient used with pooled within-class coefficients indicate the relative contributions of these features to this discrimination. The standardized coefficients are roughly equal, -0.8 and almost -0.8, which suggests that both income and lot size contribute similarly to distinguish the owners from non-owners. The reason why these standardized coefficients are interesting is because you might find that we could have found that income basically separates these two, and lot size contributes very little to that separation. In this case, both contribute roughly equally. So if we had several features, 7 or 8 features say, and we might find that 4 of them are important for classification and 4 of them don't help for classification. So that's an interesting way to help you understand which of the original features contribute to discrimination. This point is effectively that the Roy's characteristic root gives basically the same direction from the MANOVA test as the direction that we get from the canonical discriminant function. The only thing is a scaling factor, which is not interesting. So here's the canonical values that we saw before. These values, 0.18 and 0.98, if I scroll up just a little bit, are the values that come from Roy's characteristic root. And if you rescale these by -0.77, you get the same numbers. So both Roy's characteristic root and the canonical discriminant direction 1 are the same direction. All right, I held off as long as I could before discussing Fisher's iris data, and I'm going to stop the video here and pick it up in video 2.